In this problem, we have positive charge that is linearly distributed along the y-axis, extending from the origin up to y equals a. In part A, we'd like to calculate the electric field vector at point P. Point P is an arbitrary point on the x-axis. It turns out there's no symmetry in this problem, so the electric field vector has both an x component and a y component. We are going to calculate those components separately. Because this is an extended charge distribution, we are going to divide this linear shape into small parts that we're going to call dq, and each part will act like a point charge. We are going to apply the formula for point charge to calculate the electric field due to dq. That's going to be dE, and we are going to integrate over dE to find the total overall E, and we'll do that for both the x component and the y component of the electric field. Here's an arbitrary small piece dq. Its width is dy, and its vertical position is basically y. Point P is located at a distance x from the origin. That's the horizontal distance x from the origin. Now note that in this problem, y is a variable but x is a constant value because the location of the arbitrary point P is fixed. However, the charge distribution lies along the y-axis. So in order to add the electric field dEs, the electric field vectors, from each particle dq, we need to integrate over the variable y. So y is our variable, x is a constant. The electric field vector due to particle dq looks like this, along the line that connects dq to point P and pointing away from Py because dq is a positively charged particle. So let's start with the x component. The green segment on the picture represents the x component of dE. In other words, it represents dEx. So the x component of the electric field vector can be expressed like this: E sub x is equal to integral of dEx. And what is dEx equal to? Let me call this angle theta. If that's angle theta, then dEx is going to be equal to dE times cosine theta. Now, dE is the electric field strength due to point charge dq, so I'll just use the formula for the electric field due to a point charge for that. Cosine theta can be expressed in terms of x and y. Note that this angle here is also theta. Note that the dashed line, the distance between dq and P, is forming a right triangle with segments x and y. So the dashed line is the hypotenuse of this right triangle. And the length for the dashed line is equal to square root of x squared plus y squared. So let's go ahead and express cosine theta and sine theta in terms of x and y. Cosine is adjacent over hypotenuse. Segment x is the adjacent side for theta, and y is the opposite side for theta. So sine theta is opposite divided by hypotenuse, so that's y divided by square root of x squared plus y squared. Now let's go ahead and express our integral in terms of the given variables. So again, we are multiplying basically dE times cosine theta. dE is the electric field due to point charge dq, and cosine theta is x divided by square root of x squared plus y squared. What I have here is dE, so dq divided by 4 pi epsilon 0 square root, x squared plus y squared. Why is that x squared plus y squared? Because remember, we need to divide by the square of the distance between dq and the point of interest P. So that's exactly what I'm doing here. And I need to multiply this by cosine theta, which is x divided by square root of x squared plus y squared. Now this could be simplified a little bit because this expression x squared plus y squared appears twice in the denominator. First time it appears it has a power of 1, and the second time it appears it has a power of 1 over 2, that's the square root. So we can combine these, add the powers together, that will make a power of 3 over 2. That's what I'm going to do in the next step. Also, I'm going to replace dq with an expression that has dy in it, because otherwise I won't be able to integrate, right? For that, let's introduce the linear charge density lambda. Lambda is equal to total charge capital Q divided by the length of the charge distribution A. Now, so that's lambda expressed in terms of the overall total quantities. We can also express lambda in terms of the infinitesimal quantities. So if you focus on the point charge dq, lambda is equal to the charge on that small piece, which is dq, divided by the width of that piece, which is equal to dy. So dq over dy is also equal to lambda. I'm going to combine these two to eliminate lambda. It's a variable that I introduced, so I'm going to eliminate it. I'm done with it. And I'm going to come up with an expression for dq that involves the given variables and dy, which is going to be my integration variable. If you set the right-hand sides equal to one another and isolate dq, here's what you get. dq equals capital Q divided by A times dy. So in my integral, I will substitute this for dq. I will also combine the two expressions of x squared plus y squared in the denominator. And here's what I get. Now that I have my correct integration variable, I can also include the integral boundaries. Y runs from 0 to A, like so. Next, let's take out all the constants. So anything that doesn't have y in it, let's put those out of the integral, and then we'll take the integral. Now, this integral is not a straightforward one, and we can't do a u substitution. So we just look it up from an integral table. Here's what the integral table tells us. The result of this integration is y divided by x squared times square root of x squared plus y squared. Now let's go ahead and evaluate our integral. Note that the x in the numerator cancels the square of the x squared in the denominator, and the lower limit of the integral is basically 0 because y is equal to 0. So this is the answer for the x component of the electric field. Now, to find the y component of the electric field, we need to integrate dEy. And dEy is going to be very similar to dEx. The only difference is going to be the fact that we are going to multiply dE by sine theta instead of cosine theta. So it's going to look very similar to this, except here I'm going to have sine theta. So instead of x here, I'm going to have just y, but the rest is going to be exactly the same, right? So because it's dE times sine theta, and sine theta is y divided by the hypotenuse instead of x divided by the hypotenuse. So that's the only difference. And now when I take out pull out the constants out of my integral, that factor of y will remain inside the integral, unlike x that was a constant, right? So y will remain, and the integral will look slightly different, and it's going to be a manageable integral. We're going to be able to do a u substitution for this one. So let me go ahead and write that down. So here's e sub y. Again, I'm going to substitute dq with an expression involving dy as I did before. Also, I'm going to simplify the denominator by combining the like terms x squared plus y squared. Let's also pull out all the constants outside of the integral. Now we can go ahead and take this integral. We are going to use a u substitution. We're going to set u equals x squared plus y squared, and du is going to be equal to 2y dy. Here's the result of the integration. Now let's evaluate our integral from 0 to a. And here's the y component for the electric field at point P. So that was part A. In part B, we place a point charge at the location of point P and calculate the x and y components of the force acting on this point charge. This point charge has charge equal to negative q. Using the formula that relates electric field to electric force, force is equal to charge times electric field, and we will apply that to both x and y components. And here's the result. F sub x is simply equal to negative small q times E sub x. And we're going to do the same for the y component of the force. By the way, note that for the expression for E sub x, the a in the numerator and the a in the denominator cancel, so I have them disappeared here. Again, for f sub y, we do the same thing, negative q times E sub y. I got rid of the overall negative sign in the final answer, and I switched the order of the two terms in parentheses. In part C, we work out the inverse square root term for the case where x is much greater than a. So if x is much greater than a, let's rewrite this term 1 over square root x squared plus a squared. In the denominator, pull the x squared out of the square root. So this is what you get. And then I'm going to rewrite the square root term, the remaining square root term, with a negative power. Now the expression in parentheses is basically 1 plus a very small number, and the whole thing is raised to a power. We can apply Taylor expansion on this. To apply the Taylor expansion, we basically multiply the second term in parentheses by the power and omit the power, basically. And then, so this is what we get, and then we are going to multiply each term in parentheses back by 1 over x. So here's the expression for the inverse square root term. If you take this and plug it back into f sub x and f sub y, you will get the approximations given in the problem.